Hi, students. In the second part for online lecture 5, we are now going to talk about the quantum numbers. In our previous video, we started to talk about the Greek letter psi and how this was a wave function. Well, seeing that we don't want to do high-level calculus, we are actually going to build a 4-digit code that is going to tell us the characteristics that we would determine from that mathematical equation. So what we are doing is creating the quantum numbers. The quantum numbers are going to tell us various aspects of where electrons should be. The first of our quantum number is our principal quantum number n. We have seen this previously when doing the work of Bohr as to how far an electron should be away from a nucleus. This is typically also looked at as the energy of the electron as well. So our principal quantum numbers must be positive integer numbers starting with 1 and going to 2, 3, 4, so on and so forth. What this does is give us an idea of the distance of the electron from the nucleus. This means that as the number gets larger, it is further away from our nucleus and is going to have a different energy. So we could look at 3 different shapes and volumes here for 3 different orbitals. So notice that I have a principal quantum number of 1. It is going to be a sphere in the case of a 1s orbital, but notice that it has a much smaller volume than its counterparts of the 2s and the 3s. So as you can see, as I ascend in the number of my higher principal quantum numbers, my volumes have to get inevitably bigger. This is the easiest of our quantum numbers to understand as to what it is telling us. So the question you have to ask yourself is, where is this number found on the periodic table? Because we are now dealing with the size of the atom, and we are talking about the distance that electrons are from the nucleus, this principal quantum number can be found down the left side of the periodic table, listed as our row numbers. When we get to periodic trends, we will highlight this even a little more. The second of our quantum numbers is typically called the angular momentum quantum number, and this is signified by the letter L. We have only certain values that we are allowed to have for L, and they are actually dictated by our principal quantum number. So if we have a value of n, you are only allowed to have values of L of 0, 1, 2, 3, but the top limit is n minus 1. This is going to be incredibly critical for us when dealing with allowed possibilities of our quantum number. So if I have a principal quantum value of 1, the only allowed value that I'm allowed to have is 1 minus 1, which is 0, and that means that I only have one possibility for that first principal quantum number. If I then go to a principal quantum number of 2, this means that I'm allowed 2 minus 1 as my top end, so that is 1. So I'm allowed 2 possibilities of my angular momentum quantum number, that being 0 and 1. If I go to 3, notice that I am allowed 3 possibilities, 0, 1, and now 2. What happens is that this is now going to signify the type of orbital or shape of orbital that you are now going to see for that type of displacement. So what that means is that if you get an L equals 0, this is going to be the s orbital. The s orbital is spherical in shape. If you were to get an L being equal of 1, you are now going to get a p orbital. That is going to be the dumbbell-looking shape that you see in the blue orbital below. Finally, if you get an L equals 2, you are now going to get a d orbital. Notice that it looks like a 4-leaf clover, and you're going to see that there are a lot of energetic possibilities for these orbitals here in the next couple of slides. And finally, if I get L equals 3, you'll get f orbitals, and these are made famous by the lanthanides and actinide metals that you are going to see in our periodic table. So what happens is that our second quantum number talks about the shape of the volume that that electron is allowed to occupy. So this means that if I were to have an L equal to 1, the electron is actually going to be in a space that looks like a dumbbell. It is not going to be spherical, and it would not be uniform in all various directions. This is going to become important because this will help us when bonding and using different electron orbitals for bonding in further chapters. So finally, let's go to our third quantum number. This is typically what we call the magnetic quantum number. This is m sub L. So now what we are going to say is that for any value of L, so notice that for our second quantum number, we depended on our first quantum number. And now that we're at our third quantum number, we must depend on the second. We are allowed values of plus or minus L going to 0. So as I look for my p orbital, which should be L equals 1, I'm allowed -1, 0, and 1. Notice that this will give me the three mathematical possibilities of the three p orbitals that you see below. One of which is along the x-axis, one of them which is along the y-axis, and finally one of them which is along the z-axis. So it's important that we assign these different orbitals one of that set of quantum numbers. If you want to, you could state that the left x-axis orbital would be a 2, 1, -1. And then you could say that the middle one would be 2, 1, 0. And finally, the last one being 2, 1, 1. But once you assign a set of orbitals, it means that another orbital cannot have those exact quantum numbers as well. If I go to a d orbital, notice that because I've made my L larger, I now get two more possibilities. I am now allowed -2 to +2. This gives me 5 mathematical possibilities, you seeing those in the shapes that are listed below. So as we are starting to look at these quantum numbers, we are determined to try and find not only the shape, the size, but also the orientation of how these orbitals are located in our space. So the orientation means how are they pointed towards a certain direction? Are they symmetric? Do they have any nodes in which electron density cannot be? This is going to be incredibly helpful for us as we start to progress forward. Finally, let's talk about the last quantum number. We typically call this the spin quantum number, and we will talk about it more in the next chapter. But the importance of the spin quantum number is that previously we were discussing the volume and the shape and the orientation of where an electron should be. Now that we know that, the final quantum number talks about its orientation. So what happens is that our m sub s can only be a fractional value. That fractional value can either be +1/2 or -1/2. So what does that mean? Well, we know that electrons have their own magnetic field. If an electron is going and spinning in a clockwise manner, we are going to consider this an up electron or a positive electron. If it is going and rotating in a counterclockwise direction, like you see here on the right, notice that we have gone and flipped the arrow down. The important thing is that the first three quantum numbers describe the orbital, while the last quantum number actually describes the electron's behavior. So it's really important that while all four quantum numbers exist, there are going to be special caveats that we're going to have to determine about all four quantum numbers. So notice that I have my +1/2 clockwise spinning electron, and there is its counterpart. How this was done is that we were able to take an oven, heat up particles, and shoot them through a magnet using an atom beam, and all of a sudden, even though electrons were all negatively charged, we were able to split them based off of their magnetic properties, not their electronic properties. So this was a quintessential experiment to show that an electron, even though it has the same charge of being negative, can actually have two different spins that we are able to separate using the magnetic field. So let's summarize all of the quantum numbers. The first quantum number tells you how far an electron is away from the nucleus. The second tells us the shape. And as you can see, there are going to be many possibilities. So if I want a specific shape, I have to provide a specific number. The third tells you which one of those shapes the electron could be in. If you have electrons in one shape already and there are no more spots, then we have to designate to put that in a different space. Then when it comes to the fourth quantum number, you are going to see that there will be a limit as to how many electrons an orbital can have. So let us go and look at problem 310 here and see what we are able to do. What is the total number of orbitals associated with the principal quantum number of n equals 3? So this means that we must start by listing all of our quantum numbers. So we have n, then we have L, and then we have m sub L. When trying to determine our orbitals, we are only dealing with the first three quantum numbers. M sub s is to describe the electron, so we are not going to need this in this problem. So in this case, all of our answers here must have a principal quantum number of 3. So now we have to look at the possibilities of our L. Remember, L is actually the high end possibility of n minus 1 going to 0. So in this case, we are allowed to have 2, 1, and 0. So now we are allowed to have 3 different shapes. So now let us look at our m sub L. If I have a 2, remember this needs to be minus L going to positive L. So this means that I am allowed to have minus 2, minus 1, 0, 1, and 2. So in this case, with having a principal quantum number of 3 and an L that is 2, I am allowed 5 different mathematical possibilities from just those quantum numbers. So let's go and look at 1. So once again, I'm allowed to go from minus L to positive L. So in this case, I'm allowed minus 1, 0, and 1. This gives me 3 more possibilities for my orbitals. And finally, if I go to my 3, 0, because I'm allowed to only go from minus L to positive L, I can either have plus or minus 0, which means I'm only allowed to have 0. So now I will get the 3, 0, 0 orbital, and that is going to be 1 more possibility. Now I must take the sum of those numbers together, and I am allowed to have a total of 9 different orbitals. So this means that if I have the principal quantum number 3, I'm allowed to have 9 different possibilities of putting electrons into those orbitals. So let's try one final problem, and that is, which of the following sets of quantum numbers is forbidden when describing an atomic orbital? So now I give you 4 possibilities of quantum numbers. Being forbidden means that you are breaking one of the fundamental rules. So let's look at what one of those forbidden listings could be. If I go and have 1, 1, 0, 1/2, I can now point to the fact that this term right here is my violated term. Because remember, L must be less than n minus 1, and it's not. So we would consider this a forbidden electronic possibility. So now let us go and look at our 4 candidates. Notice that I have a 2 for A. My second term is correct. Then I would have plus or minus 0. So this is a correct quantum number set. If I go to B, I can have the principal quantum number of 3. This means that for the second quantum number, I'm allowed 2, 1, or 0. I have a 1. And then finally, for my third quantum number, I'm allowed minus 1, 0, and 1. I have 0. So this is a good quantum number set as well. So let us go to C. I have 4. Now I have 3, which abides by my n minus 1 rule. If I have a 3, I'm allowed -3, -2, which I have in this case, and I'm allowed to have a downward facing electron, which is going to be -1/2. This would be a good set as well. If I look at D, I have the principal quantum number of 5. So I'm allowed the possibilities of 4, 3, 2, which I have a 2. If I have a 2 for my second quantum number, I'm allowed -2, -1, 0, 1, which I have, and then finally I would have another downward facing electron. So this is a correct set. So E is going to be our correct answer, that we are allowed to have all of these quantum number sets. So let's go and look at another forbidden possibility. So what happens if I were to say that I have 2, 1, -2, 1/2? Notice that it would be the third term that violates this here, because normally I'm allowed to only go from -L to our positive L. Well, in this case, our -2 exceeds our L, so this would be an incorrect term. So as you're looking through these problems, look at the various examples and make sure you follow the quantum number rules to make sure that the numbers in your code, which describe electron behavior and their location and possibilities, is going to be correct. Have a great day.